Okay, so yesterday we reviewed, guys, we reviewed plotting points on a coordinate grid, X and Y values. And then we looked at applications, plotting those. We talked about whether we might join points up for certain applications or leave them not joined. So when they're joined up, we call it a continuous set of data or a continuous relation. And if we don't join them up, it's called discrete. Okay, so now we're going to look at, does it form a straight line, which we talked a little bit yesterday about as well. If it does, then there's a special word for it called linear. And it kind of makes sense. If you take a look at that word linear, it's got the word line within it. So a linear relation describes a relation that forms a straight line when you graph it, which means it has a constant change, rate of change. So yesterday when someone, I think, what was it? A car was traveling 100 kilometers no, it wouldn't be per minute. Well, let's say a car is traveling 100 kilometers per hour, then that's at a constant rate. Okay, so if we were to graph that after 1 hour, they've got 100 kilometers. After 2 hours, 200. It would form a straight line. Okay, so we want to look at these, and just a reminder here what that is in words. When a linear relation is graphed, it forms a straight line. That means a constant change in one quantity, the independent, produces a constant change in the related quantity. Okay, so they have to be constant. It doesn't have to be the same change, but you can see as I go from 0 for x to, let's do, looks decent here, 5 for x, I'm going up 3 to get to that point. So if I look down here, it's the same rate or close because I estimated. So it's a straight line. Really, you don't even have to look closely. If it's a line, that's a linear relation. This is not a linear relation. It's curved. It's kind of a U shape. So that is not. And here, if you put a ruler along there, would the points lie on that ruler's line? Yeah, it would. You can do it better because you have the paper version. If I do a line here, it looks like it is. Sometimes depending on the scale, it's a little bit hard to tell, but it looks like if I can be accurate with my line. Oh gosh. There we go. They're all on the all the points are on the line. So that is linear as well. Okay, so with graphs, it's really quite easy to tell. With tables of values, it's a little bit harder. So that's where we have to look back at this part of the definition. A constant change in the independent variable produces a constant change in the related dependent. Constant means remains the same. So here, if I take a look at each of these. So each of these, as I go from 1 to 2, 2 to 3, I'm increasing by 1. So that means that my change in my dependent, the y, if it's linear, has to be the same amount each time because these are all ones. So here, if I look, it's plus 3, and this is plus 3. So far, that's linear. I need to check all, and they're all the same. So for an increase of 1 in x, y increases by 3, always. So that is linear. Constant change. Okay, you can say of 3 for each increase of 1 in x. Okay, take a look at the next one. Put these little notes like I'm doing on your paper so you remember. So now I'm increasing by 2 each time. Okay, so those entries are all 2s. Do you need a pencil? Can you get it out, please? I never got the one back from yesterday, actually. Okay, so plus 3, plus 3, no, sorry, plus 3, plus 5. This is plus 5. All of these are plus 5. Okay, so it's a constant change here, right? 5 units for every 2 in x. So what is the constant change really? Would be 5 over 2 for every 1 unit. Okay, but it doesn't really matter. I'm not asking for what the value is. It's just a constant change in the y for every constant change in the x. Okay, and all of those values are the same. Now we get to a different situation. We've got plus 1 there, plus 2 there, plus 2 there, plus 1, plus 3. So those are all different. That doesn't mean it's not a linear relation. It just means maybe we're skipping some values in between. Okay, so all I've done is look, okay, 1 plus 1 is 2, 2 plus 2 is 4. So I've written out the change in x. Now I'm going to write out the change in y. So that's plus 4. What's that? Plus 8. That's plus 8. That's plus 4. And that's plus, what, 30? That's plus 12. So those are different. Again, it doesn't mean it's not linear. We have to see for every change in x, is it consistent all the way? So here, I want to look, my hint is always look for the ones that maybe you might have the same change. So going from 2 to 4 and 4 to 6, I'm increasing by 2 each time. So going from 9 to 17 and 17 to 25, is it the same increase? Yep, it's going up 8, up 8. So though that part of it, we know from here, 2 to 4, 4 to 6. So that part's linear. Is the rest of it. So let's think about that. If you go increase x by 2, y increases by 8. It's proportional if it's constant. So if I increase by 1 in x, what do you think y will increase by? 4, exactly. Basically, it's that value, the y there, the change in y over the change in x. We're just not using notation for it. So here it was 3 over 1 is 3. This would be 5 over 2. This would be 8 over 2 is 4. Okay, so let's look. Does that make sense? If I'm going from 1 to 2, I'm increasing x by 1. I'm going from 5 to 4, I'm increasing by 4. Yep, so that part's linear. Okay. Same thing here. If I'm increasing by 1, I should add 4. So that part now is linear. Now we just have to test the last line. So if every increase of 1 in x is 4 for y, what would be an increase of 3 in x? That last line there. Elliot? 12. And it is. Okay. So if you plotted these on a graph, they would all form a straight line, right? All of those points. So this is linear. Again, constant change. And if you want to do that, what we said was 8 divided by 2 was 4. Okay, so that one took a little bit more work. Let's take a look at the next one. We're going up by tens now. So plus 10, plus 10, plus 10. Now here is just up 5 and 5. Okay, so let's do the same on the right. So 8 minus 2 is 6. 6 minus 2 is 4. 4 minus 2 is 2. 2 minus 1 is 1. 1 minus 1 is 0. So you just label all those changes. And then look for the constant changes on the left. So those are all by tens. Is it constant on the right? Yes. So for sure we know the first part of that is linear, but we have to check the whole table. So now if we go up 10 in x, it goes down 2 in y. So now 5 is half as much of that, right? It's proportional. So now if I'm going up 5, that's half of 10. So half of -2 is -1. So that part works. And same with the last one. So because there's both 5s. So that one is linear as well. What the constant change would be is actually now in the right -2 over 10. Sorry, just the computer's catching up. So -2 over 10, or you can look at the bottom there, which is -1 over 5. You weren't asked for that constant change, but that's what it would be. Okay, next one, what are we doing? We're adding 2 here. Until we get to 0. Then we're adding 1. And we're adding 1. Okay. What are we doing to the y's? Well, we're adding, what's that, 6. We're adding 6. We're adding 6. We're adding 6. We're adding 6. Okay? So you might think, oh, all the y's are changing the same amount. That's linear. But take a look. All the x's weren't changing the same amount. So this part up here is linear, but not this part, because that changed to be adding 1 each time, whereas y changed the same amount. So that is not linear. Okay, next one works. Adding 5, adding 5, adding 5. All of them were adding 5. So that's a constant change in x for all of them. That means if it's linear, we have to have a constant change in y. So that's +2. But now that's +4. So right away, I know it's not, because I'd already done the change in x. So +8, this is +16, this is +32. So right away, I know it's not linear. Blue. So neither of these, not a constant change. Okay. So it's a little bit of detective work, a little bit of just looking at the table of values, change in x and change in y, and finding that ratio. Now, at the bottom, I just have, instead of a table of values, I have ordered pairs. So we want to compare, same thing, the change in x. So I have to look at the first numbers. So that's +1. That's +1. That's +2. Okay, that doesn't mean it's not linear. Okay, it just means that we've got different points along the way. But then I'll change to a different color here. Then I want to look at the y's. So from 9 to 14, I'm adding 5. From 14 to 19, I'm adding 5. And then, so that's linear, okay, the first 3. But now when I'm adding 2 to x, what happens? Let's check. I'm adding 10. Is that twice 5? 10 twice 5? Yeah. So that is linear because it's proportional. So the rate of change, oops, so here. So the constant change of 5, right? 5 over 1 is 5. 10 divided by 2 is 5. So that one is linear. I'll circle that. So same with the x's here. -2 to -1 is adding 1. -1 to +2 is adding 3. 2 to 6 is adding 4. So they're not constant, but that's okay, depending on what y is. So now, what happens? 9 goes down to 2, so we've subtracted 7. 2 goes down to -19. So what's that? That's -21. And then -19 down to -47. So 47 minus 20, that's -28. Okay, so now we have to do a little bit more work in this one because the x's the change in x wasn't constant. So this is saying when we increase 1 in x, our y decreases by 7. Okay, so that's where we'll start. Now if we increase by 3, it should be decreasing by 3 times this. So if I multiply that by 3, do I get -21? I do. This one's +4, so if I multiply that by 4, do I get -28? I do. It has to be proportional. So this actually also is a linear function, or linear relation. You'll talk about functions in 10C. A little bit more to that. Okay, so you're always looking for those proportions. So turn over the page. Oh, that's it, right? No, there's another page. What happened? Just a second. Oh, it just skipped on my thing. All right, so this is kind of the same as yesterday. Fill in the table of values. Okay, so you're going to substitute 0 in for x, 2 in for x. I'll give you a few minutes to do that. Okay, so I've got the table of values. I'm going to check if they're linear. So these are all increasing by 2. And so that means if it's linear, these should all be the same amount. So it doesn't mean you have to always show the work like this, but in your head, you have to count up by 4s because all the x's changed by the same amount. And so, yep, that's linear. Then the next one, I'm going increasing by 1, by 1, by 1, by 1, all by 1s. So that means these have to be the same. So that's by 3. Are they all up by 3? Yep, they sure are. So that's linear. These are all up by 1s here. But take a look here. You can see right away, they're not going up by the same amount each time. So this one right away, I can tell that it's not linear because these are all up by 1s. This is up by 3, by 5, by 7. So it's kind of a pattern, but it's not the same amount for each increase by 1. Okay, so that's not linear. And here, up by 6, up by 2. So these aren't going by the same amount, but that doesn't mean it's not linear. this is where you want to look, okay, where are some constants? So up by 4s. So I want to look at these to start. So that's up by, that's subtracting 16. There, to go from there to there, and then subtracting 16. So that middle part is, so every increase of 4 in x is a decrease in 16 in y. So now if I'm going up by 2's, it would be half of 16, which would be 8. Yep, so that's negative 8. And this down 8. Yep, that works. And then this is by 6. So if for every 2 it goes down 8, then every 6 it would go down 3 times 8, which is 24. And it is. So this is linear. Okay, so you have to think proportions back from junior high for this. Now take a look at the equations, because I gave you those equations. That's how you got the table of values. What do you notice about what's different about this equation compared to the other ones? What's something that's different? Both got y, all of them have y equals. All of them have an x in it. But what's different about this x term? Brayton. It has an exponent. That's exactly right. So anytime it has an exponent that's not 1, we don't normally show an exponent of 1, right? Because this really does have an exponent of 1. We just don't show it. So anytime it has an exponent that's not 1, it's not linear. Okay? So non-linear equations have an exponent on x that is not 1. Okay, in this case it's squared in that third one. It could be cubed. It could be to the 10th. It could be a negative 1. Okay. So in the linear equations, we have an x term, guys, at the back. We have an x term. Exponent on x is 1. We don't have to show it. And we might have a constant term. So we had a +1, we had a -2, we had a -1, and that's okay. All right. Oops. So it says, now the last thing is now we're told that they are linear relations. So that means it must have that constant rate of change. And we have to fill in the missing values. Okay, so take a look at the patterns in this. So we're going up by 1 each time. So you don't have to show it if you don't want. Just take a look and see, is it going up by the same amount? If it is, then everything in the y's has to go up by the same amount. And so what is it going up? It's going up by 2, by 2. So we have to keep going up by 2. So 16, 18, 20. Done. Okay. Sometimes we're not given the first y's, we're given in the middle, but we do need 2 in a row in order to figure out what that constant change in is. So take a look here. Are these are all going up by the same amount? Okay, they're all going up by 2's. Okay, so that means we need all of the y's to be constant. Take a look at the one that's given to you. We're going down 10. So that means we have to go down 10 to get the next and the next. Okay, and so up here we have to think about what we would have to go down 10 by to get negative 10. Well, that would be 0. And so going upwards, basically we're doing the opposite operation. We're adding 10 to go up. So then you can check. Go down 10 works. Go down 10 works. As long as those changes in x are the same. right? Take a look at the next. Up by 1, up by 1, up by 1, up by 1. This is up by 4, so we just have to be a little bit careful. But all the other ones are up by 1. So look at the y's that are given. This is up by 4. Okay? So if that's up by 4, and this is linear, it has to be the same. For every increase in 1, we have to increase by 4. So this would be 16. This would be 20. But this last one, the x changed by 4, not 1. So 4 times as much. So this has to be up by 16. Okay, 4 times 4 is 16. So that's going to be 36. That's something you have to be very careful of. So part of being good at math is good attention to detail. So you don't want to just look at a few and see the pattern going up by 1s and stop. That goes up by 4. Filling in this last one, it obviously has to be 4 less. Opposite operation. Okay. Next one, same deal, except now we're missing an x value, so we have to work back from the y. But here, take a look. So we're going up by 3, going up by 3, going up by 3. Doesn't mean that we're going up by 3 here, because that goes all the way to 27. Take a look at what we're given here. We're going up by 15. Okay, so that means for every increase of 3 in x, we go up by 15. So if I can do the next one here, -5 plus 15 is 20. I can work backwards and have this be -35, because I've got to go up by 15 for each. Okay. Okay, David, ask me, please. Stop turning around. What's the question? Oh, is 10. Yeah, thank you. Yeah, so just put up your hand, right? Don't tell Braden, tell me if I make a mistake. Sorry, add 15 is 10, yeah. Okay, but now to go from 10 to 40 is up by 30. Well, that's twice 15, right? So we have to do twice as many x's. We have to add 6 here. It's all proportional, so that would be 15 filled in. Okay, just going to erase this from the other because it gets a little bit confusing there. And now from 15 to 27 is what, up by 12? Okay, so if the last was up by 6 and this is up by 12, I've got to do twice 30, which is 60. Okay, so that's going to be 100. Okay. So now, the tougher part, guys, is question 6. State an equation for each relation. So these are linear. So we know from what we learned above that it's going to be y equals something x. No x squareds, anything like that. And take a look. We need to look at those previous questions, number 3. So here, the constant change was 4 divided by 2, which is 2. Take a look at the coefficient of x is 2. Here, the constant change was 3 over 1, which is 3. Take a look at the coefficient of x is 3. Here, the constant change is -8 over 2, which is -4. So whatever the constant change is the coefficient of x. So that gets us part of it. So in the first one, the constant change is 2. Maybe we'll have to add or subtract something. Let's leave that for a sec. Next one, what's the constant change? It's negative 10 over 2, right? Because these x's were all increasing by 2. So that's negative 5x. Here, let's look at the 1. So increase of 1 was 4. So that's going to be y equals 4x plus or minus something. Here, 15 divided by 3 is 5. So y equals 5x. So that gets us, so that change in y over the change in x is the coefficient of x. Now, let's go back again. We've got to learn from our examples here. Take a look. When x is 0, we put 0 in for x, and we get 1. So if you have a point in or a set of pairs in your table of values where x is 0, that will tell you what the constant term is in your equation. Because you're putting 0 in for x. Okay, so it's always that value. So take a look here. I made sure I put that in. So when x is 0, y is 10. So that would have to be plus 10 there. Because when I put 0 in for x, that first term goes away. Here, when x is 0, y is 10. So I've got to have plus 10. When x is 0, y is 16. So I've got to have plus 16. When x is 0, y is negative 35. So those are your equations. So now you could, if you have a graphing calculator, you could do this. I'm going to get mine out here and show you. You might not have a graphing calculator yet, and you don't need to have one for this course. You will for 10C. So if you're going to do 10C, it's a good idea to get one now, so you can get used to it. Okay, so you don't have to know how to do this yet. It's not really part of the curriculum. I'm just doing it for you. So what I'm doing is in a graphing calculator, I can enter that equation, y equals. So where do you find that? If you have a TI, it's y equals. Okay, a Casio I'll have to show you separately. So you can see it, I'm circling there, y equals, and then you enter 2, x is that red selected button, plus 10, and then you graph it. Okay, so now if I were to enter or graph along here, if you trace along, you'll see when I first press trace, it goes to the point 0, 10. Well, that was one of our ordered pairs. If I press 1 now and enter, it'll say invalid, so go to, because it's too big on our, oops, sorry, I said 1, enter. No, it goes there. I put 11 by mistake. So 112. You can't see it on the graph because I need to change the window, but 112. You did 2, you get 214. So it kind of confirms the fact that we got the correct equation. You don't have to do that. But next semester, if you're taking 10C, you will be doing lots more work with graphs of linear functions, and you'll be learning your calculator stuff. Okay.